Welcome to the Agilent Technologies technical video tutorial. Today we're going to talk about something called Automatic Fixture Removal, which will allow you to remove probes and other fixturing structures that you want to remove from a device under test. In this case, we have a probe station and a vector network analyzer, and we will show you step by step using an application called Physical Layer Test System that will allow the user interface to be very simplified and follow these simple steps. Very often there are higher frequencies that are attenuated through these unwanted fixtures, and there's many different types of error correction that can be done, but not all of them are as accurate as you might imagine. And so to get the ultimate in accuracy, we have found this automatic fixture removal process to be extremely accurate at very high frequencies. So take a look, see the step-by-step process, and by the end of this, it should be extremely clear how to do this type of error correction inside your signal integrity laboratory.
Let's start by describing the bench measurement system that we have here. We are using Agilent's Physical Layer Test System to control a 20 gigahertz 4-port vector network analyzer. The network analyzer is cabled to our printed circuit board bench probing system. The probes make the connection to our printed circuit board test structure. We have a camera system here so that we can see our miniature ground signal ground coaxial probes and make accurate connection to our printed circuit board. Taking a closer look at our printed circuit board device under test application, we see that we need to make a connection with our coaxial cables from the network analyzer to the planar surface of the printed circuit board and onto the transmission line. We could use a connector, but in this case, our small ground signal ground coaxial probes provide a consistent, high-performance connection to the printed circuit board. Now we will go through the step-by-step procedure for removing the fixturing from the measurement of a DUT structure. The DUT that we will be measuring is a simple 50 ohm transmission line with a 25 ohm impedance discontinuity in the middle, and we would like to remove the fixturing connections from that measurement and be left with just the impedance discontinuity. The automatic fixture removal calibration will use an electronic calibration short open load through calibration reference plane at the end of the VNA coaxial cables, and then a measurement of a simple 2x distance symmetrical through transmission line to get the electrical data for the port 1 and port 2 probe to PCB fixturing. Now the DUT can be inserted between the PCB reference planes at port 1 and port 2. The DUT is a simple impedance discontinuity going from 50 ohms to 25 ohms and back. The eCal SOLT removes the coaxial cables from the measurement, and then the automatic fixture removal removes the port 1 and port 2 fixturing, leaving just the DUT impedance discontinuity. Before starting our network analyzer calibrations and measurements, it is important to make sure that the network analyzer cables can easily reach the device under test and the measurements we will be making. You can see here that we've added tape to make sure that the cables stay in place and there will be minimal movement during our measurements. We have also labeled port 1 and port 2 to make sure that it is clear when we are taking measurements which port we are on. Here we are showing how Agilent's physical layer test system can be used to set up the VNA. First we set up for a 2-port DUT and then select the calibration procedure. The default VNA setup is optimized for a balance of speed, accuracy, and conversion of frequency domain data to the time domain. When connecting the electronic calibration module to the network analyzer cables, it is important to follow some general connector care requirements. Here you can see we blow off the connections before mating them. The precision connectors should be easily connected together with finger tightening. Then, in order to get the proper torque for a repeatable connection, it is important to use 2 wrenches. One wrench is used to keep the cable from spinning, or also to keep the mating connector from from spinning. The torque wrench provides a repeatable, consistent connection to the coaxial cables. Now we will select the electronic cal module for calibrating out the effects of the cables on port 1 and port 2. The SOLT with eCal is selected for port 1 and 2, and then Modify Throughs is selected to change the through to unknown to minimize cable movement and improve the calibration quality for this automatic fixture removal application. PLTS will then indicate the steps needed for calibration, with blue being the next step, green a completed step, and red not yet done. After connecting eCal to the port 1 cable and then to the port 2 cable, it is time for the unknown through connection. Here we are connecting the unknown through for the last step in the calibration. The unknown through has the advantage that we do not have to move port 1 and port 2 cables of the network analyzer, and the unknown through reaches from one port to the other. The other advantage of the unknown through is that when the calibration is done, we can measure the unknown through and use it to validate the quality of the calibration. With the unknown through cable connecting the port 1 cable to the port 2 cable, PLTS can now finish the final calibration step, and the CalSet data is saved as eCal SOLT and automatically stored on the VNA. A measurement of the unknown through with the newly saved eCal SOLT calibration can be used to verify the quality of the calibration. PLTS controls the VNA to take a measurement and then displays the selected frequency domain S parameters. The typical S21 loss and S11 reflection is verified, and then the data is converted to the time domain for verification of impedance and connector discontinuities. The data is normalized to 50 ohms for the impedance display, and then the reference levels and units per division are set to the desired resolution. Now that we have finished the calibration to the ends of the network analyzer coaxial cables, we can attach the microcoaxial probes. Again, we use the two-wrench system to hold the coaxial cable from twisting and apply the proper torque. The microcoaxial probes have a very small and delicate tip with 1 millimeter spacing on the ground signal ground tips. We therefore need a precision XYZ positioner for accurate placement of the probe tip, and it is always important to know which direction is up so that the probe tip can be lifted without damaging it. There is also an adjustment for planarity, and this can be checked by landing the probes on a soft gold surface and looking for the 3 ground signal ground probe marks. Now we'll be making a measurement of the 2x symmetrical through. The 2x symmetrical through has the same connection on port 1 as port 2, and using PLTS's automatic fixture removal, we'll be able to move the reference plane from the end of the coaxial cable to the middle of this through-line structure onto the printed circuit board. Here we demonstrate the skill required for landing the microcoaxial probe with 1 millimeter spacing between the tip of the ground wings and the signal pins. As the probe is lowered to the clean PCB surface, one watches for the shadow to meet with the probe tips. As the probe gets close to the PCB surface, final adjustment of the X and Y positioning can be done. Then very slowly the probe is lowered another 1/4 to half turn on the controls, and a slight forward sliding motion is visible as the probe makes contact. The probe can be lifted to verify the planarity of the probe marks and adjusted if needed. Now we'll use a nice feature that PLTS has for taking measurements. It actually turns off the calibration and provides fast sweeps so that we can see when our probes are landed and we've made a connection. Here we have an open, and as I land the probe, the connection is made and we have contact. Now we can proceed with the actual measurement. Once the electrical connection to the 2x through PCB structure has been verified, then PLTS can finish the measurement and import the data. A quick look at the frequency domain S parameters shows the expected low loss and minimal reflections of this 50 ohm through path. The data set is then saved as 2x symmetrical through for use later by the Automatic Fixture Removal utility. It is always useful to convert the data to the time domain and verify the symmetrical through has the same port 1 and port 2 discontinuities and that there are no loose connections or fabrication mistakes with impedances. The next step is to apply the automatic fixture removal to the 2x symmetrical through using its own electrical data to determine the port 1 and port 2 probe to PCB fixturing effects. Removing the fixturing places the VNA reference plane at the middle of the through line, and the quality of the calibration can be verified by comparing the results to that of an ideal zero-length through with no impedance discontinuities and no loss. The effects of the automatic fixture removal can also be viewed in the frequency domain. When the fixture removal is turned on, the losses approach 0 dB for all frequencies, and the reflections get much smaller. The automatic fixture removal utility makes it easy to turn the removal on and off to see the benefit of removing the fixture from the measurement. Any lack of symmetry from port 1 to port 2 on the symmetrical through line will affect the quality of the calibration. Now that we have finished measuring the 2x symmetrical through and verified that the automatic fixture removal technique is working, we can now measure our actual device under test, which is simply a 50 ohm transmission line with a 25 ohm impedance discontinuity in the middle, and on either side we have the test fixture connection going to the probes. Once the connection to the dot impedance discontinuity structure has been verified, PLTS can finish controlling the VNA to take the measurement. Selecting the frequency domain S21 and S11 measurements of the dot and then right-clicking on the graph to auto-scale the data provides a clear view of the quarter wavelength resonances caused by the length of the 25 ohm impedance discontinuity. In the time domain analysis of the data, the impedance reflection data for port 1 and port 2 are selected, and then the data auto-scaled for checking the symmetry of the probe to PCB connections for fixture removal and verifying the expected 25 ohms dot impedance discontinuity. Now we go to the Utilities menu and select the Automatic Fixture Removal tool and apply the previously measured 2x symmetrical through to the measurement of the dot. This removes the probe to PCB fixturing from the measurement and provides an accurate measurement of just the dot impedances and electrical length. In the frequency domain, the removal of the fixturing provides better resolution of the resonances caused only by the dot impedance discontinuity. Turning the automatic fixture removal on and off clearly shows the benefit of removing the fixturing effects and moving the measurement reference plane onto the PCB for measuring a PCB structure. In summary, we have successfully demonstrated moving the reference plane from the network analyzer onto the printed circuit board for the measurement of a device under test with a 25 ohm impedance discontinuity to successfully show just the electrical performance of the dot. This simple technique shown here for a 2-port device is also applicable to 4-port differential measurements.
So if you found this video tutorial helpful for the signal integrity engineering work that you're doing in your lab today, Agilent Technologies would like to invite you to take a look at our technical library on our website at www.agilent.com/find/PLTS. And we'd also like to acknowledge the thanks and help that we received from our partners, Verigy, Gigatest Labs, and Wild River, for the fixturing and also some of their applications knowledge. Thank you very much.